Hi. So as he said, even though I could not hear very well from the back, I'm Francesc Campoy. And I'm going to be talking about what I've been working on since I left Google. So I'm sure you've all heard this phrase, software is eating the world. And it's something that everybody says, but I had not noticed how true it was till recently. I found an article that contained basically the scale of the lines of code that we've been using over time. So you might, I do not remember this, I'm not that old, but you might have heard about Photoshop. The first version of Photoshop had 128,000 lines of code. And this seems like a lot to me, even though there was no colors, though, so kind of weird. I do remember this one, Windows NT 3.1, with 4 to 5 million lines of code. And this is already an OS. Like this, you do things with this, like you play Prince of Persia and stuff. So this serious stuff. Then you have this, Apache OpenOffice, 9 million lines of code. It's like, OK, so that starts to be pretty big. And then you get Chrome. The latest one has 18 million lines of code. That starts to be a lot of code. I'm sure you recognize. Windows XP, 45 million lines of code. I decided not to count Vista, because I didn't want to think about it. And that didn't work. What happened there? Oh, sad. This car, 150 million lines of code. And when I think about driving a car with 150 million lines of code, everything I can think is of a slide that I used a long time ago at GopherCon when I did the opening keynote about understanding Neil. This. 150 million lines of code that are driving me over the road. That sounds dangerous. And then, of course, Google. How many do you think it has? Like 1 million, 100 million? 1 billion lines of code. And that's what they say. I'm sure there's more than that. But I do not work at Google anymore, so I cannot comment. And the thing is that the tools we've been using to write code have not evolved over time that much. If you think about it, many people still use Vim, which is a great tool. I'm not saying it's a bad tool. But what I'm saying is that we should have more powerful tools that allows us to write code better. Not only better code, but also to be able to write code in better conditions. Having assists, like when you're driving a car nowadays, if your car is not too old, probably it's going to warn you about things like, be careful, you're getting out of the road, or you're going too fast, or there's a car right in front of you, you need to brake right now. Maybe it will brake for you. Maybe it's a self-driving car if you have enough money. Like all of these things are happening in many, many places, but not in computer science. We still keep writing code basically the same way, then reviewing it basically the same way. We have continuous integration and continuous deployment, which is great. But until then, the tools have not changed that much. And the thing is that depending on the tools you're using, you can use them for really cute stuff. Like you can build this beautiful little doghouse. And that's great, right? So I'm not saying those tools are useless. What I'm saying is that those tools are great for some scale. But when you go into a larger scale, you're going to need better tools, right? So that's why I'm here today to talk about not machine learning in Go code, but machine learning on Go code. Most of the code that I wrote, don't hit me, was in Python. I know. But also, there's a lot of code, don't worry. So yeah, not in Go code, on Go code. I am Francesc Campoy. I'm VP of Developer Relations at Sourced, which is pronounced Sourced, not Sourced, but everybody says Sourced, so I'm considering just changing the name of the company. Who cares? And before that, I was a developer advocate working at Google with the Go team and the Google Cloud Platform team. Also, I'm on Twitter and on GitHub. And you might have heard about my YouTube channel. If you're interested on machine learning with Go code, like doing machine learning, writing Go code, that's where you should go, not here today. And I'm the second most popular channel in the world, yay, for Go. You know. OK, so we're going to be talking about, first, what is machine learning on source code? What is that thing? Does it make sense at all? How do you do it? What do you do? What are the tools? Then we're going to be talking a little bit about the research associated to it. Machine learning on source code is still a very active research field. So most of the time, what I'm doing is actually reading papers and trying to figure out how those techniques could be applied to computer science and to software engineering today. And we'll be talking about those use cases. And finally, we'll talk a little bit about why I think could be the future. Also, I just noticed I have a timer. Cool. OK, so what is machine learning on source code? Machine learning on source code is machine learning that you do on source code. Easy. So what it means is that the input to the model that you're training, rather than being text or images or video or any of those things, is source code. That's pretty much it. That means that you can basically apply any other technique that you've used before in machine learning. It's nothing completely new. There's actually many fields that are related to it. But it's about the fact that we're trying to extract information that is specific to source code. If you think about source code, it kind of looks like natural language, but it's much more strict, right? When you're generating Shakespeare, if you generate a weird sentence, you can say it's art. If you generate a weird Go code, it will not compile, right? So the constraints are pretty different, but the skills and the techniques that you use are actually quite similar. So what are those fields that are related? So one of them is data mining. As I was saying at the beginning, we have huge amounts of lines of code, billions of lines of code, trillions probably. I tried to find, if anyone works at GitHub, I would like to know how many lines of code there's in GitHub. I could not find that on OctoHub? I forgot the name of the thing. Whatever, those stats that they release once a year, I could not find that data. I'm sure they don't want to publish it for some reason, but just let me know. There's also natural language processing, as I was saying. There's a lot of the techniques that we use to understand humans that we can also use to understand programs. Because at the end of the day, what we're doing most of the time is trying to discern in between what you meant writing the code and what you actually wrote. When there's a difference between those two things, that's when you have a bug in general. You can think, for instance, when you have a for loop, if you try to iterate over all of the elements, and instead you end up iterating over the indexes, you actually meant the elements, right? But the computer don't care. You're going over the indexes, that's what's going to happen. And finally, there's a lot of graph-based machine learning. And this is the scary part, because graph-based machine learning is super complicated. There's a lot of maths, and when you read a paper, if you've ever done anything related to graphs, you might remember all of the very complicated language to describe graphs and vertices and all of these things in mathematics. So imagine that and then put machine learning on top. Super fun. So what does this require? What do you need to do machine learning? Well, first of all, you need lots of data. This is machine learning. Machine learning is just learning by example. You need to throw a lot of data at it, and it will eventually learn stuff. And yeah, you really, really need lots of data. If you just have the Go standard library, for instance, which I've been playing with and trying to train models on top of the standard library, you get something interesting, but it's actually not enough data. You will end up with interesting things that we'll see later, like copyright of the Go team. Yay. It will just appear randomly, because all of the files have it, so all of the files will have it. So you just write it somewhere in the middle. And also fancy ML algorithms. We're going to be talking about some of them today. Do not worry too much if you do not know what a convolutional neural network or a neural network, all of these things are. That's totally fine. We're going to be talking especially about what those mean to you, developers. And finally, you need luck. These statistics, the probability of something working is, high, but not 100%. So if something fails, just run it again. We're developers. We're used to that. OK, so first challenge of machine learning on source code is retrieving all that data that I said we need. There's two data sets that I know that are very useful for this. There's GHArchive. I think they cannot use GitHub itself, the name, so that's why it's called GH. But it's basically just an archive of all of the repos on GitHub. It does not contain the code itself. It contains all the metadata, and then you can go clone stuff and downloading things. Then we have public Git archive, which is something we created at source. And basically, it's getting GitHub archive, getting all the repos that have 50 stars or more, and downloading them, putting everything together, and just creating a really, really big zip file. It's not a zip file. It's many, many files, but it's around 4 gigabytes of data. So this is normally what we use to start doing machine learning on some source code. It contains many different languages, all of these things. So it's a pretty useful place to start. The tasks of machine learning are actually quite different to what you would expect in natural language processing. One of them is the fact that before you start with anything, you need to know what programming language you're using, right? You cannot say, oh, parse this program. You first need to say, by the way, this is Go, parse this program, right? So we have tools for that. GitHub has a tool called Linguist. We have a tool at source called, we call it Henri, because it's something related to French from My Fair Lady, if anyone knows that movie. I have not watched it. Then we need to parse those files once we know the language. And we want to do that in the most language agnostic possible way, which is interesting because parsing a language in a language agnostic way seems incompatible, but actually it's not impossible. The whole point is we're able to get ASTs that have all the same format no matter the language. Not the same content, obviously, but just the same format. Basically, we define a protocol buffer for ASTs, abstract syntax trees. Then we need to extract things from them. So if you want to say, I want to extract all of the function names, because that's one of the things that sometimes we want to learn is about function names or variable names. You want to extract those. So we do with XPath. And then we have reference resolution. It's something that we don't do, but Google has a very cool package project if you're interested on these kind of things. It's called Kite, and it's super cool, even though the documentation is not that good. And finally, we also want to not only analyze the current state of the source code, but also the evolution. And this is going to help us understand how the code evolves itself, so we can then predict things about not the current state, but the future state. And that's something that we need to do all the time. We have GoGit, which is a Go library to use Git. It has a very cute logo, and I have stickers for those, so find me later. We created this thing, which I don't expect you to understand completely, but here, if you look at language right there, that is something that identifies the programming language given a file and its content. Then you can do many things, and this, for instance, counts how many lines of code per language we have in the Go repository, github.com/go/go. Turns out that our first programming language is Go. The second one is text, and then assembly, which kind of makes sense. You can also do things like this and count how many functions you have. So that is, you're getting the language, we are parsing it with that UAST, that's Universal Abstract Syntax Tree, and then we're extracting things with XPath, this expression right here with role function, role declaration. And this is something that we have it as a website, and you can check it out. And this is why I went to bed yesterday at 3 a.m., because I was fixing bugs. So we just released it today. You can go check it out. And this is why I didn't sleep much. So once we have these data sets, now what do we do next? OK, so when we have all this data, we need to analyze it. Cool. But what is source code? This is source code, sure. But what does it mean to analyze this source code? Well, it really depends on what you're trying to do. You can analyze this source code as a series of bytes, right? This UTF-8, you can do that. You can go character by character and try to understand things from that. You can also get every single token. So package is a token named package token with the text package. And then there's an identifier named main, and all of these things. And then you can predict things based on tokens. This allows the neural network to have a better understanding of the structure of the program, so you will end up with better quality predictions at token level. But it will never generate new variable names, for instance, because it only generates things that it has seen before, right? So you need to decide which one you want, and sometimes you can use both. You can also consider source code as an abstract syntax tree. Warning, the abstract syntax tree doesn't match the code. Do not try to match them. That will not work. But this is an abstract syntax tree of a variable declaration saying var a equals 3. You can see the var a equals 3 at the bottom. Those are the leaves. Those are the pieces that appear in the code. But then also you have the structure. Now, this is way cooler, because you can learn many things from this structure. You have way more information in here, and machine learning, what it does is just predict things out of the information you gave it, right? It does not create information. So this is much better. But now the problem is you have trees. So you need to learn from trees, which is hard, because you need to do recurrent neural networks over trees, which is super hard. I've tried, failed, but I will keep on trying. And then you can do, well, we have static analysis. Static analysis techniques are very powerful, and there's some other forms of expressing the same content of the source code, but annotating with more information that is very useful. So for instance, this is a control flow graph that allows you to see what the program is actually doing, where you can jump from line to line, and things like this. You can also think about the possibility of learning from, let's say, the SSA generated by the Go backend. That's also a thing that people do. There's research about this. You can also learn from things like a compiled Java class, or you can learn from just a random, any kind of format. You might get information from there. So there's all of these things are things that people are trying to learn from. And depending on what format you choose, you're going to be using different techniques. So yeah, we can have sequence of bytes, of tokens, trees, or graphs. So it keeps on getting harder and harder and harder. So now that we decided how to use it, how do we learn from this? Neural networks. And I'm not going to try to explain what a neural network is, other than it's a magic piece of statistics that is able to learn stuff, basically, through the power of gradient descent. So basically what it does is you have some inputs, and then it generates an output. And it starts randomly, and you start saying, no, the output should be this. And then it tries to fix itself. And then you continue saying, no, the output is this, no, the output is this, until it learns. It's kind of like a puppy, but in a computer. So for instance, if you have MNIST, which is the hello world of machine learning, what you're doing is you're getting a 26 by 26 pixels image. You're breaking into pixels, and that is your input. So 784 pixels. And then you're putting all of those inside to the machine learning thing, and then it generates something from, basically it generates a vector with 10 positions. Every single one is a probability for the digit, right? And at the end, you choose the one that has higher probability. So this one is basically saying that looks like an 8. That's basically what a neural network does. The important thing is that it's around 0, but not necessarily 0. And that's something that I'm going to use later on. So how could you use it for ML Encode? The same thing. Well, you could say, I'm going to get the previous 9 tokens, always 9 tokens, and I'm going to try to predict the next one. And this is something that you can do, and it works, and it's pretty cool. And it seems pretty useless, but wait for it, because it's actually good. If you want to deal with not fixed sequences, but like a sequence that might be longer than that, and you might want to generate extra sequences, then you're going to need to use recurrent neural networks, which are basically a neural network that fits itself. So it's kind of like recursion, but for neural networks. And this is something that you can use, for instance, to translate French to English, and that's a very funny joke, bonjour les gaufres, which means hi waffles, not gophers. So how can we use this for ML Encode? The typical example is the character recurrent neural network. This is something that you give it a bunch of characters and try to guess the next one. And you keep on feeding it over and over and over and over. Typical example is to teach it how to speak like Shakespeare. It actually works really well. It's surprisingly good. So of course, what I did was I taught it the Go standard library. And I tried to see what happens. And I was able to achieve 61% accuracy, which is not great, but it's actually not that bad. So let's see the results of this. This is before training. This is what the neural network things looks like. So, I mean, not exactly, right? But it's a good effort. This is after one epoch. An epoch is just seeing the whole data set once, right? So it just parses the whole standard library once. And this looks good. Like, look at that. If error is not nil, return error. Yay, we have Go. Like, that is clearly Go. So with that, I was like, OK, so this looks promising. Let's continue. This after 2 epochs. And it starts to do weird things that kind of look like Go, but not really. And then after many epochs, it gets a little bit better. But generating code is kind of a weird thing, because the thing with generating natural language is that if you get it kind of wrong, it's kind of fine. But if you get wrong programs, they're just wrong, right? So that's the problem. Generation of code of program is actually a really hard problem. There's much more research about this. Miltios Alamanis from Microsoft Research has basically all of the papers I've read. Like, I'm a fanboy of him now. And he talks about this VAR misuse task, where given a program, we remove one token, and you need to guess which one it was. And this is actually very useful. And the cool thing is that this is a very simple problem to explain, but a very hard one to solve. So it's a very good place to do benchmarks for research. Uri Allen and what's his name? Aaron Yahav from the Technion University, I think, and they created this thing where they're trying to learn from the program, but by encoding it to embeddings. Embeddings are a very cool thing, and they're able to actually predict, doing an embedding over function names and code, what is the function name that you should give to a piece of code, which is really impressive, and it works quite well. And if you want to see more research, we have a repo for this, awesome machine learning on source code, and there's a lot of papers in there. You will not finish them, I'm sure. OK, so now, what can we build with this? So if instead of trying to predict things, we try to figure out whether something is predictable, we're changing a little bit the game. Because now, rather than trying to say, hey, give me the next token, I want to give you the next token, and you tell me whether you think that's right or not. So imagine that you have a very, very, very large code review. By the way, I'm super proud of that Go PR thing. That is not Photoshop. That's actually Google Slides. So yeah. So imagine that you get this really big PR. You're going to need to read all of it. And you're going to need to pay attention to every single line of code. Now imagine that you're using this neural network to let you know what is the most unexpected piece of code in here. Basically telling you, you know, the rest looks kind of boring, looks fine. But this piece of code looked interesting. Not wrong, just interesting, unexpected. And it tells you this, right? This is one of the things we're trying to build. Imagine with VAR Misuse that you can identify that there's a bug in this program. Can you find it? This is a copy-paste error that I myself have done. The second defer, that's defer from close, not defer to close. I'm sure you've done this before. Static analysis for this is hard to find. But actually, with VAR Misuse, it will detect really easily that that is wrong, because it's not what it expects. And this is something that already works. This is something that IntelliSense has been adding to Microsoft. So Microsoft has been adding to IntelliSense. And it works really well. And they have found a bunch of bugs with this. What if we can recommend names for functions? So for instance, the one on the left and the one on the right look very similar. But thanks to code embeddings, you can actually figure out that the one on the left should be contains or has or something like that, because it returns a Boolean, while the second one is more like find or index or things like this. So if you're writing some code that ends up doing the wrong thing, you can actually figure out. You can say, are you sure that you want to do this? So when you put all of that together, what you get is something that can do assisted code reviews. And an assisted code review is not an automated code review. Assisted code review means that you have someone reviewing code that will have a bunch of tools at their availability in order to review code faster and better. And this is something we're working on, and we released the first version, but I'm not going to talk much about it, because what we did is like an automated formatting tool that learns the rules of formatting of your code and then reapplies them. The problem is that we have GoFumped, so it's pretty useless. But if you write JavaScript, it's cool. And there's much more than that. So we're working, as I said, on automated style guide enforcing. We're working on bug prediction. Once you have all the history of a repository, you can actually try to predict which is the next line of code that will change. You can also predict, according to all of the things that we've seen before, that line of code tends to change to this other thing. So maybe you want to change that. And we've seen that that actually works really well, specifically for when a new version appears of a library. For instance, let's say that you go from I'm going to say Angular, why not? From Angular 1 to Angular 2, and it would be able to tell you, oh, OK, so we know the differences that exist, and this is the PR that you should write. This is something that we're working on. It's actually very exciting. And it will hopefully also work for Go soon. And automated code review. Imagine if you could have raw Pike as a service. I used to work with the Go team, right? And that experience of learning from the Go team, reviewing my code, was probably the most useful experience I've had at Google, by far. Imagine if you were able to extend that to the rest of the community. Not by multiplying the ROBs, which is hard, but instead by having many robots that keep on learning from the code reviews that are already happening. And in the future, code generation, why not? So from one of the typical things is, well, I write the unit test, you write the rest. Could work, we don't know. The problem is that then you need to write good unit tests, which is probably harder. You have also natural analysis, so trying to describe code. We've got to the point where you can search images by text, and also given an image, we're able to describe it. We're working on doing the same thing with code. So imagine that you get a piece of code, a function, and let's say it writes documentation for you. This is something that is doable. It is hard, it requires a lot of data and a lot of computation, but we're working on that too. So, will developers be replaced? Will developers be replaced? Also, the secondary question is, will this create Skynet? The answer is probably. No. Developers will be empowered. That's the idea, right? Like, what we're trying to do is not to replace developers. Architects were not extinct when CAD appeared. When AutoCAD appeared, that didn't remove architects. What it made is that architects were way more powerful and able to create more interesting things. And that's what we're trying to do. So if you want to learn more, Source.tech, that's my company, not SourceD, but Source. And we're hiring. Also, awesome machine learning on source code for more details on all the research that I quickly mentioned. That's my email, and come say hi, I have a bunch of stickers. Thank you.